So as I mentioned, we're not going to stay in chapter 1 for too long as it's an introductory chapter. I'm in a hurry to get to the good stuff. So you are responsible for reading chapter 1, read it, check the PowerPoints. We're going to look over it, see if there's a little bit more that we want to glean from it. And the idea behind machine language and writing code and what happens there is very worthwhile talking. So we are going to do that. If you're also in my fundamentals course, it's going to be a little bit of a, but I don't think anybody is trying to take that at the same time since that's a prereq for this. So what is machine language? Did I draw the box, chip in the box, and did I do that diagram? Okay, so anyways, we have a dude in a box and he's got some opcodes that he follows, which are instructions. And we wrote a language for him that had like 3 opcodes, I think. Read, add, and write. And so really, those were being given to him as numbers. So the way that your computer works is that it's all a series of numbers. And then those numbers are fed to the chip, and it does some stuff, and it writes numbers back out to memory. So it's all done by numbers. And underneath it all, it's all done as binary. And so a whole bunch of ones and zeros are written into your memory and your hard drive and stuff like that. So even before we had these nice fancy electronic silicon chips, that is the way that computers worked in the 40s, is that the programs were a series of opcodes. And whether they were entered into the program by actual dials, on a computer, that would be really old-fashioned, or fed in as a paper tape or a magnetic tape or a series of punch cards or whatever, then you were entering in opcodes and numbers that those opcodes worked upon. And that is machine language. And we're going to give it a little silly example of machine language here. This is not for a chip. It's for a light bulb. We have a light bulb, and we've decided that we have 1, 2, 3, 4, 5, 6, 7, 8 commands, opcodes that it supports. If it's all zeros, it means stop the program. If it's a 1, it means turn the bulb on. If it's that number, which is a 2, it turns the bulb off. If it's that number, which is a 4, it dims the bulb. If it's that number, it brightens the bulb. If the bulb is fully on, skip the next instruction. If the bulb is fully off, skip the next instruction, and then go to the start of the program. And so somebody has written a little program that uses these machine codes. And so if we wanted to, we could watch the bulb lighten and dim according to all this, executing the program. Decrease the brightness, decrease the brightness, decrease the brightness, increase the brightness, and so on. So there we go. This is a machine language program. It's all numbers. And you can convert these numbers from binary into decimal numbers, so that you could actually see, what it looked like. Like I said, 1, 2, 4, and 8, and so on. Let's see if we can find another example. Machine language example. Something more in a light bulb. What's this look like? All right, again, this is not for a chip, it's for a motor. Jump past the sensor and the constant locations. Read the right sensor value here. Read the left sensor value here. Right to the motor power level, so we're controlling a motor. Apparently we have 2 motors. We have a left motor and a right motor, and we have a left sensor and a right sensor, and we are controlling the speed of them. So here is our series of commands for it. That's all that machine language is, except it's expressed as zeros and ones. So when your program is ready to run, there's a file on it, written on your hard drive or your flash memory or whatever, that is then loaded into RAM, and then it's fed into the processor, 1 opcode at a time, in order to execute. We don't want to write code in the form of numbers. That's what they had to do in the 40s. Is that the efficient way of doing it? Well, you get a very fine-grained control over the processor, but nobody writes machine code like that unless they absolutely have to. And you can be sure that large video games, for the PlayStation or whatever, or large applications, any application anymore, is not written in machine code. It's written on a level higher up, known as assembly. And here's what assembly looks like. I'm just going to pick one at random. All right. So if you're playing PacMan and you get to level 256, the game crashes effectively. It doesn't stop running, but it draws a screen like this, and PacMan can eat a certain number of dots, but it can't eat 256 dots because you know there are 256 dots on the screen. And so this is a kill screen. You reach that screen, you can't go any further, so the game does have an end. And it's extraordinarily likely that the guy who programmed PacMan did not realize this bug was here, and he just didn't care because he didn't think that anybody would ever play 256 levels of PacMan. On the other hand, it's probably a good thing that that bug is there, because if you could play 256 levels of PacMan, you could probably play 256,000. You might play for a week and then die of exhaustion or something like that. So you know, it's nice that there's an end to it. But people being the way they are, you know, they wanted to fix it. And so this person figured out how to fix it. And this is a page dedicated to his fix. And other people have fixed it as well. And if you like playing old video games and you install an emulator, a video game emulator on your computer so that you can load up old video game files and play Space Invaders and PacMan and old Nintendo games and stuff like that. Anyways, what you're getting are these binary files, these machine language files. But what those machine language files were made from assembler. This language is assembler. And we see that assembler is all these little acronyms, these 2 and 3 letter codes. Add, load, increment, jump, return, decrement, all of those. Those are a lot easier to remember than just a series of numbers. We can see the numbers down the side, you know, that these lines of code produce. But the programmer would create a text file full of this stuff. And then he'd run what is known as she would run what is known as an assembler, which would take this assembly code and convert it to the machine language. And then the machine language is the executable file, or what you burn to metal, you know, to a chip or whatever, in order to actually execute it, or what you upload to the App Store or whatever. So every single line here is commented here, because the guy was trying to figure out what the code did. And it's not a bad idea to comment every single line of code if you're writing assembler, because otherwise, you know, if you just have this, it's really hard to follow. We're not going to talk about the fix for it at this. It's a curious little problem, though. Why does it crash at 256 and not level 254 or 3000 or something like that? Why is it that specific number? It's interesting. We'll talk about that at a future point. So you've got machine language, which is all numbers representing opcode and data. And then you have assembly, which is abbreviations, mnemonics, you know, words that represent the opcodes to make the program easier to use. And use an assembler program to turn that assembly into machine language, which we'll call object code. So this is a low-level language. Assembly is a low-level programming language. I put that in the wrong place. I wanted to put it right next to the word assembly. Yeah. And yeah, it's better to write this stuff, jump and sub and add and things like that, than it is just to write these pure numbers like that. But it's still hard. You'd rather write it in an English style programming. You'd like to see English words and algebraic expressions. You don't want to have to load C with a value of A and then add with an add statement like that, and increment. You know, this doesn't look like math statements. It is performing math, but it doesn't look like math statements because it's controlling a processor with opcodes rather than being expressed in things like A is equal to 2 times 20. We would like to do algebraic expressions and English Although if English wasn't your native language, you might wish it was Russian or whatever. Commands. That's a high-level language. And there are hundreds of those. C in C++ is a high-level language. And so you have statements like A is equal to 2 plus B if A is greater than 10, print something. We kind of did a print statement. Print, okay, whatever, you know. It's a high-level language. That looks a lot better than that did, right? And yeah, you could convert this into a high-level language. But in the 80s, in the 70s, you didn't have a lot of memory on these chips. And so you coded your video games in assembler. All PacMan and Donkey Kong and all the old Nintendo, 8-bit, 16-bit games were programmed in assembler. But it's not an easy way to manage it. So you can be sure that nowadays most video games are programmed in higher level languages, usually C++. Just because C++ is something that produces fast code as in comparison to a lot of other programming languages, and you want your code to be as fast and efficient as possible if you're programming for a video game system, right? Because you want to get the frame rates as fast as possible, whatever. I don't really need 2 notepad files open. Okay, so say you've written this file. That's not a real program, but we're going to pretend that it is. You would have to put int main in front of it, and whatever. You'd have to put all the rest of that stuff. You have to put the right syntax, so semicolons in the right places, blah blah blah, whatever. You save that as a file, as a .c file. So that is your source code. It's not code as in I performed an encryption because I don't want anybody else to read it. It's just a term that people use to mean that you're taking, an idea that you have and you're expressing it in the form of a computer language. People call it coding. Completely different than, an algorithm for, encryption where you're trying to make sure that, the government doesn't spy on your email or whatever. So you save your file as a .c file. .c is the source code. Then when you're ready to run it, you click the green button. No, you didn't have a green button in 1970. And nowadays, it looks easy, but what's really happening in the background is the compiler compiles the .c file and creates object code, which is the machine code, the machine language. And do you need to know all this stuff? Well, you don't have to run the compiler by hand. You don't have to run the next thing that I'm going to talk about, which is the linker by hand. But you can, and you may wind up working on a system where you don't have these nice fancy visual, development environments where you're not clicking the green button in order to build your application. And you really are running compilers and linkers in order to get your C code, to work. After you've compiled it, it creates object code. The object code are .obj files. So if we save this as my.c, that was our file name, then after we ran this, the file name would be my.obj. Then you run a linker, because an obj is not an executable. You're familiar with Windows that your programs are called .exe. So the linker takes the object file, and you may have hundreds of object files in a large project. You may have thousands. I don't know how many there are in a huge application like Word or whatever. But the linker combines the .obj files into an executable. And even if you're using a Mac or, phone or something and it doesn't create a file with a .exe extension, it's still an executable file. In Linux, you don't create something that has .exe at the end of it if you don't want it. Instead, it's got a flag that marks it as being an executable file. And you can get a directory listing and see which files in that directory Linux or Unix are executables. It doesn't have to have a specific extension. The Mac's the same way, but they use a .app extension to indicate a folder that contains the executable file. So anyways, that's what happens. You write some source code, you save it as a .c file, you run the compiler on it, you run the linker on it, and now that you have an executable, then you can run that. So that creates my.exe, and then you can run my.exe, and it'll print out your answers, or you type in your numbers, or whatever you were supposed to do with it. Now this stuff gets handled by our Visual Studio, our IDE. You know, when you press the build button, it runs the compiler, and it runs the linker. So you don't see that happen, although you can scroll down to the little output window and you'll see the results, or it'll say build successful or something like that. But these concepts are important. If there's a syntax error, then the compiler is not going to work. I am recording. Yes. Okay. If only one of the files compiles correctly, but you have more than one file, then you'll get a linker error if it tries to link the files, and one of them is missing. It can't find all of the files to stitch together to make your executable. Or if you open somebody else's project but one of the CPP files is missing, then the linker is not going to be able to run, even though that the files that were there did compile. If you use another language, if you go on to take Java, or you're using Python or something like that, this is not the process that those languages follow. This is the C process. The other ones work differently. A lot of languages work by creating an environment that loads your C file and then compiles it and runs it on the fly. And that's the way that Python works, and that's the way that Java works, and C# works. So those languages are not compiled languages, or they're not strictly only compiled languages. But C++ certainly is. Has a compiler and a linker in it. If you want to, you can run these tools by hand from the command line, but you can't just do cmd and then run cpp or whatever the compiler's name is, because it doesn't have all of the environment set up properly. But there is an icon, there is a program that will set up all of that programming environment so that you could then run your build scripts by hand if you ever needed to do that, if you wanted to do that. We're not going to bother. Some programming courses would make you do it all by hand. You would create your CPP files with an editor, not with Visual Studio, but with a text editor of some kind. And then you would run a program called make, and the make would be configured in order to run the compiler, or you could run the compiler by hand. So you could do all this by hand. Sometimes I ponder making us do that at the beginning so that you just appreciate the IDE, but hopefully me talking about it has convinced you that you'd rather click the green button. So the computer only executes machine language instructions. Machine language instructions are just numbers. We don't want to write programs in machine language. Programmers got tired of that real fast, so the first computers were built in the mid-40s. Very quickly, by the 50s, people were inventing programming languages, compilers, and things like that. So there are low-level languages written in binary machine code or assembler. High-level is closer to human language, meaning that you have your algebraic expressions and your English keywords. There are lots of programming languages. The ones invented in the 50s include Fortran and COBOL. The ones invented, C was invented in 1970 based on some earlier languages that were invented in the 60s. And then there were languages that were invented in the 80s, like C++, and Python, I think, came around like in late 89 or something like that. And then there were languages that came out in the 90s, like Java and JavaScript. And I don't know when Ruby came out. BASIC has been around since the late 60s, but it's dramatically different now than it used to be, so that you can create big applications, windowed applications. You can create Visual Basic. Pardon me?
So I thought Python came out in the 2000s.
Let's look. I could be wrong. All righty. 1991. When did it start gaining in popularity? Probably considerably after that. So the year 2000 may be prominent in its popularity, but he originally published it earlier. Conceived in the late 80s, implementation came in 89. When does that mean that he actually... Alrighty, 2.0, the big version, the one that started getting popular, came out in 2000. So you're correct in that. Okay. Why are there so many different languages? Because people learn some programming languages that don't do exactly what they think that it should do, or they think that they can do it better. So for example, Java is kind of a cleaned up version of C++. Takes the syntax and removes a lot of weirdness from it. And yeah, so we're using a language that has a lot of weirdness in it, but that's okay. We can learn it. We're tough. And then Microsoft started using Java and put support for it in their Visual Studio and their other applications, but they extended the language. They made changes to it so that if you wrote Java code for Windows, it wouldn't work on any other computer. Microsoft likes to do things like that. But the company that created Java had a copyright on it. You had to license Java from them, and so they sued Microsoft, saying you can't make your code do different things than what our standard says. And so Microsoft said, ha, no way. They removed Java, and then they came up with their own version of Java, which does things a little bit differently, and in their minds a little bit better, and so C#. So that, languages keep coming up because people think of different ways of implementing them, and they want to, use a different paradigm in order to, there are functional programming languages, and there are imperative programming languages, and there's all sorts of buzzwords, different programming styles. So from a high-level program to an executable file, you create the file using the program with a text editor. And I skipped a step. Before the compiler, something called a preprocessor runs. And do you remember we did #include up at the top of our code? #include takes a file and it inserts it into your file temporarily. If you open your file, it's still just as you wrote it. But for purposes of compiling it, it brings that file in and puts it there so that you can use the contents of that file as well. And so the preprocessor runs first to handle all the #includes. And not all languages support preprocessors. In fact, it's a very uncommon idea. Then run the compiler that takes what the preprocessor made and turns it into OBJ files, machine instructions. Runs the linker to convert that OBJ file into an executable file according to the format that that platform requires. Steps B through D are usually performed by a single click. Errors detected at any step will prevent execution of the following steps. Source code, preprocessor, which modifies the source code. The compiler runs on that, creates object code, the linker, the executable. Am I going to be talking about object code after today very much? Hardly at all. Just know that in the background, if you went looking, you would find some .obj files that match the file names of the code that you write. And that a linker comes along and makes an executable from those OBJ files. So an integrated development environment gives you all the tools needed to write, compile, and debug a program into a single software application. And these were actually kind of a big deal when they came out, late 80s. Examples: Visual C++, Turbo C, Code Warrior. That's a Mac version, but it's a really old version. You can tell that this textbook was written in the 90s because Macs use something significantly different now. And here's our example of our IDE. It's just one, but it happens to be the one that we're using in this class. You write your code. When you're ready to build it, you click on the build over here, or if you click local Windows debugger, it'll probably build it for you and try to run it right on the spot. You can compile your code in two different ways. You can compile it for debugging or for release. If you compile it for debugging, it includes a whole bunch of stuff that helps in figuring out what's going wrong. If you compile it for release, it strips all that extra fluff out, and so you get a much smaller executable. When you give somebody else one of your executable files, you're going to want to compile it as release for a couple of reasons. One is that, it's smaller code, it probably runs faster. And another is that all that debug information could be used to reverse engineer your code. And that doesn't matter if you're just writing a little executable, I don't know, modifies your game files to change the stats of your character or something like that. But if you're writing commercial software, you don't want a competitor to be able to figure out what your program is doing based on the debug code. That would give them a great big head start on writing some competing software to yours. And of course, hackers love it when people send out the debug version of their code, because they can very easily, reverse engineer how it works. Reverse engineer means that you take that executable and you switch it back to being code, right? So that you can then modify it and make it do other things or figure out how it works, find security flaws in it. What is a program made of? Sugar and spice and everything? No. Common languages in programming. You have keywords. Programmer defined identifiers. Operators, punctuation, and syntax. Those are two different things actually, right? Because in the English language we have punctuation, like commas and quotes and stuff. And then we have syntax, which is the order of the words. Like in the French language, your adjectives typically follow the nouns. So you don't have a red tractor, you have a tractor red in French, using the French words for red and tractor, right? So that's their syntax, that's their grammar. Some languages have, the upside down question marks at the beginning of the sentence, or, all sorts of different symbols. So keywords are the words that define the language, the functions that the language supports. Words like if and while. We'll get used to the keywords, about 80 of them, of which we're going to use about 15 or 20 of them. A lot of them are kind of in a rarefied. Here we go. Here's our program. There are some keywords here. Int is a keyword. Using is a keyword. # include is a keyword, but it's not a C or C++ keyword. It's a preprocessor command. Double is a keyword. Return is a keyword. So when you're looking at this kind of program, in the editor tries to color code it for you. And you can change the colors if those colors are not to your liking. If you have color blindness of some sort and red and green are kind of nebulously mixed together, then maybe you'd want to make your comments blue or something like that, or put it on a black background rather than white. Stuff like that. Some people spend hours customizing their the colors. You can waste a lot of time configuring your tools. So anyways, this is color coding the keywords. The keywords are the blue things. So everything blue here is a keyword. Is it blue a magic? I mean, it's just a color chosen to make it visible. The color itself is not important, and you can change it through the configuration. And then the operators, like these arrows, and the parentheses, and multiply, apply, are put in a different color. The punctuation, for some reason, is in the same color as the arrows. The punctuation includes things like semicolons and commas. I forgot what all they said. And then identifiers. I've already been using the term variables. I think we use variables in, pay and hours and rate to calculate somebody's payroll. The hours, that's a variable. It has a programmer given name. The programmer decided that that variable was going to be called hours. Is the variable name important? As far as the computer is concerned, it doesn't matter what the variable names are. You could call this Fred and Wilma and Barney. You could use stupid variable names like that. Or you could call them A1, A2, A3, A4, and make your code completely incomprehensible. Variable names are important to you and other programmers. You choose good variable names to make your code easy to understand. The easier your code is to understand, the easier it is for you to fix it, to make it work, to remember what it looks like and how to get it to work if you need to make changes to it later. So don't just use A, B, C, X, Y, and Z in your variable names. Now when I'm typing code in up here, I may use single letter variable names because they're easy to type, right? And we don't all type, at 120 words per minute. But you should choose good variable names, that are words, not just single letters. So those are known as identifiers. There are other identifiers. Function names, like name, is also an identifier. And there are rules for what kind of identifiers, how you can name them. You can't put spaces in your identifiers. You can't use first space name equals Joe. You have to do first name without that space equals Joe. You could put first underscore name, or you could use a capital letter in there to make it easy to spot, but you can't have spaces in your variable names. That's one of the rules of the syntax of the language. And another is that the variable name cannot start with a number. So you could have taxes 1989, that's legal, but you couldn't put 1989 taxes. For whatever reason, they just made that a rule. So you have your keywords, things like if, well, I guess we could go back and look at this thing, find them. This didn't have a lot of keywords in it, actually. Int, double, and return. Let's add those to that little thing here. If, int, double, and return. And we'll learn what all these keywords mean, exactly what they mean. There's a lot of them we won't learn just because this language has lots of keywords. Programmer-defined identifiers include things like variables, file names are another identifier, and functions, and there are other things, classes, and methods. We will learn what those are as well. Operators, they're standing by. Plus and minus and multiply and divide, those are all operators. There's another one which is percent. There are those things, we use those, the arrows, those are operators. Using ampersands and two vertical bars and equal and not equal, those are all operators, and we will find out what they all mean. If you've written other programming languages, you know pretty much what a lot of these mean already. However, that looks pretty alien if you're a Python programmer because that means and, this means or, and an exclamation mark means not. And that language actually uses the English words, which makes it easy to read. C++ doesn't care if it's easy to read. Punctuation. Those are like the commas that you use in order to separate variable names, or the opening and the closing braces, or parentheses. When you make a function call, you have to have parentheses and in parentheses. Those are all part of the punctuation. And then the syntax. Every statement has to end in a semicolon with certain exceptions, and, just the rules that the language has to follow. For example, if you're going to multiply these two things, your hours worked times your pay rate to get a total paycheck, it has to be this times this equals pay. You can't say hours times rate equals pay. Sounds good, but according to this language and a lot of other languages, the syntax requires that the value that receives the calculated result is on the left-hand side, and that the expression that gets calculated is on the right-hand side. And if you try to reverse them, it doesn't work. Now, does hours have to be before rate? No, you can swap those. That's syntax independent. But the variable that you're assigning into has to be on the left, and the expression that you're going to assign into it has to be on the right. That's an example of syntax. So keywords, those are reserved words. You can't use those words in your programming language. You can't use the word if as a variable. You can't say if equals 79. You can't say while is equal to Joe. Those are reserved words. You can't use them as your own variables because they mean very specific things. And our language doesn't really support the idea of reserved words. Or I guess it does. For the most part, a person's name should probably not be a verb, right? Yeah. So what is your baby's name? Well, his name is Compile. You know, what? You know, okay, you're a real nerd. Why would you name your baby that? Or his name is Shop. Or, you know, his name is Kill. You know, things like that. You wouldn't give your baby a name that matched the name of a verb, right? You can't give your variable names of reserved words. You can't call your functions any of the reserved words. So they have a special meaning. They cannot be used for any other purpose. All of these are some of the reserved words, also known as keywords, that particular code snippet illustrated. And it looks like we are going to be going through this slide by slide. This is good information. I'd forgotten that this was a really good chapter rather than just what is a computer. You make up your programmer-defined identifiers. Since your program is going to be manipulating data, that data needs to be stored in your program in order for you to manipulate it, and you need to put that data into variables in order to give it names so that it's easy to refer to, right? Name, first name is equal to Joe, last name is equal to Bob. You know, first name and last name are the variables, and you want to give them good names, not just X and Y. So they're not part of the language. You use them to represent things, data, variables, which are memory locations, functions, etc. And we've seen in this snippet of code, similar to what we did on Thursday, 3 variables: an hours, a rate, and a total pay. Operators are the symbols. You have your math symbols. There's a couple of other ones too. There's percent, which means modulus. We'll talk about modulus. I'm sure that y'all remember from CIT 1113. And then there's the assignment operator. The assignment operator allows you to put, a value into a variable. And then there's another one involving the equal sign called the comparison operator. That checks to see if a variable is equal to another one. And those two things are different. If you say x is equal to 3, that means you're putting the value 3 into x. But if you do x is equal to 3, it means you're comparing them. Is x equal to 3? And when I'm reading out source code, I'm not always going to differentiate correctly between a single equal and a double equal. You'll need to figure it out by syntax, by context. Are we assigning a value? If we're assigning a value, you use a single equal. Are we using an if statement or a while statement? In that case, you're going to use 2 equal signs. And this language will let you use equal signs in the wrong place. If I write some code like this, if x is equal to 3, that's going to compare x to 3, and if it's true, it's going to do what's underneath it. But if I do this, if x is equal to 3, like that, a lot of languages don't let you do that because that's probably not what you meant. You probably didn't mean to erase x and store the value of 3 inside an if statement. C doesn't care. It's happy to let you do that. The C++ compiler at least gives you a warning about that. But you don't want to, and I have typed that, within the past 2 or 3 years, and you get really frustrated trying to figure out why your program's not working because you missed a single equal sign. So punctuation are semicolons between our variable names, right? We declared 3 variables, hours, rate, and pay. We put semicolons between them. That's part of the punctuation. Punctuation and operators are different, right? Arrow, 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 equal sign, and the multiply and addition and subtraction are operators. Punctuation is just the periods and the commas and the stuff like that. So syntax is the rules of grammar that must be followed when writing the program. The syntax controls how you use the keywords and the operators and your variable names and your punctuation, what order you have to string them in. You have a lot of flexibility, but they do have to follow rules. It'd be like if you used the French order, the tractor red, and nobody could even understand you, right? Fortunately, English and the human brain is capable of understanding, so that if I said I'm going to drive the tractor red to work, you'd think that was weird, but you might be able to figure out that I really meant red tractor. And computers aren't like that. They need to follow the exact syntax. And making a computer understand that kind of loosey-goosey syntax that we like to use in the English language is a big deal. That's why people make a lot of money. You know, artificial intelligence programmers get hired by Google and Apple and Microsoft and whatever in order to turn plain language into something that can be operated upon by a computer. But our programs don't do that. We can't tell it what we mean and have it magically work. We actually have to tell it what to do. So variables are named spaces in the computer memory. Not only that, but we're going to give it a little bit more of a strict definition. A variable is a named place in memory that has a type and contains a value. What does has a type mean? It means what kind of data is stored in it. You could have an int, an integer, a whole number. You could have a float, and there's another type of a float, a more precise float called a double. Those are 3 different types. You could have a string. That's another type. So if you have this, age is equal to 32. Well, in this language, you have to define your variables before you use them. So we would have to say int age. That's not true of Python. You could just say age is equal to 32 and say, okay, great. If you do not define your variables, then you can't use them. If I went around and then typed in, if I made a typo, age is equal to 40, like that, that's going to be an error. I think that this is the same as that, but it's not, and this is an undefined variable. Never did I define anything called AAGE. So you have to define your variables before you use them. Forgive my typos. Alrighty, so the type of this is an int, the name of it is age, and the value of it is 32. So hours held the hours worked, rate held the pay rate, and pay used the gross pay. Was the result of the calculation. So you define your variables by giving a data type and then listing one or more variables. We could have listed all these on separate lines. We could have done this. Double hours, double rate, double pay. One per line. They would all need to be lowercase. It's just because Office likes, you know, to change things to uppercase when you don't want to. So you could do it like that, or you could put them all on one line as long as they're the same type. Double, like I said, is a floating point type. We will use the word double. We will use the data type double rather than float, just because it's more precise. Why is it more precise? We'll talk about why.
Is there a limit to how many you can assign, or you can?
You're never going to hit the limit. It's probably in the thousands or the hundreds of thousands or something like that. It builds a table when it's being compiled. And each variable that the compiler hits gets a new, addition into the table. And I'm sure that those tables do not have a small limit. But that's a really good question.
Well, and also too, like on one line, if you're separating them by commas,
then you can go to the next line if you need to, and to the next line, and to the next line.
It's fine.
Right, that's fine.
Okay.
So, very good point. The Python folks are used to spacing being incredibly important. Everything has to be tabbed just right. This language, the spacing, is there for your benefit, but it's not that important. If you want to define a variable like that, and then you feel like defining something else like that, and then you feel like putting a couple of, things on a line like that, and, maybe you feel like defining, another variable over here, like that, or if you feel like doing something silly like, like that. That is valid code in this language as far as defining variables is concerned. In Python, you remember that would totally break it. that everything had to be lined up on the same level and stuff like that. And the same is true for if statements. If you do this, if age is less than 32, well, in Python you use the colon, in this one you do not. Here we use, the curly braces, and instead of a print statement, we're going to use the fancy C++ thing. Okay, so that's valid code. But we could also do this. That's valid. Or if you wanted to, you could do this. Would you do that? No. Your C program, you could take out all the character turns pretty much, except for the preprocessor commands. And you could have one line of code that contained a million statements that you would have to scroll over, for hours to see the end of. Are you going to do that? No. But you could. So this is what's known as whitespace. You use your whitespace judiciously to make your code easier to read. But anywhere you use a space, you could also use a character turn, or you could use a tab or whatever. So the syntax for your white spacing in this language is much more lenient than it is in some programming languages. But like you asked, is there a limit to how many you could define on a line? No, I don't think you'll ever hit a limit. You could have hundreds of variables defined. If you're going to have hundreds of variables, you probably do it in a different way. So the word double specifies that the variables are floating point numbers and they're double precision. Kind of like a double wide trailer, right? It contains twice as much room. A double wide float contains twice as many bits in it. It's an 8-byte data type rather than a 4-byte data type, meaning they can hold much more precise numbers and much larger numbers. So input, processing, and output. Looks like we only have 3 more important slides here. 3 steps that a program generally performs. Gather your input. In this class, we're going to gather our input from keyboards or from files on a disk drive. Process the input and display the results as output. Well, if you're displaying the results as an output, that kind of implies that you're sending it to the screen. So I don't know if I would have broken it out like that, but because writing to the file is not a form of display. But you will produce output. You gather input, you process the input, you store it as output. So you gather your input based on what they type, and you store what they type in variables, or you read it from a file on the disk drive, and what you get from the disk drive you will store in variables of various types. Then you process it, you add numbers together, you do this, you do that to the data, and then you display the results or you save the results to a file. Typically, a program loops so that it continues to run until the user wishes to stop. The programming process. Define what the program is going to do. Visualize the program running on the computer. I like that term, visualize. I'm going to visualize. The computer is going down. Whatever. You just have to figure out what the program is supposed to do. And how do you figure out what it's going to do? You get written requirements. You use design tools like flowcharts and pseudocode. Check the model for logical errors. What you try to do as much of your work before it gets coded. The more work you do up front, the less time it takes to code. The farther along you discover a problem, the more expensive it is to fix it. If somebody gave you bad requirements and then you spend, a week writing a program and then you give it to them and then it gets put into production and nobody notices that mistake until the customer gets it and then they demand, a fix to it and you've already gone on to other things. It takes a lot more time, a lot more expense to fix the problem late in the game than early in the game. So when I give you code or when I give you an assignment, typically, I'll give you a short definition of what the program is supposed to do. And it's up to you to figure out how it's going to do it. Usually I'm not going to give you a flow chart or pseudocode or stuff like that. We're beyond the point where you need that kind of hand-holding. I might give you a screenshot of how it would look if I was going to write it, but that doesn't mean that you need to make yours look exactly the same. If the screenshot is there just to help you understand what I want the program to do. but you can revise it. You could change, those aspects. You type the code in, you save it, and compile it. I like this. It's like this thing on South Park where, he writes a 4-point plan. Point 1, do something. Point 2, do something. Point 3, and then a whole bunch of question marks. Point 4, profit. And leaves off the question marks. This doesn't say how you go from changing, a model into code. But you create some source code based on the logic, based on the pseudocode. You're writing your own programming language, statements that solve the problem that we're given here. You correct any errors found in the compilation. You fix all the syntax errors. You run the program. You look for logic errors. You test your program. You give it test data. You correct the errors found when running the program. As you correct those, you may introduce syntax errors, which have to be created, so it's kind of a cycle, And then it turns out that you had the wrong specifications in mind, or I gave you the wrong specifications, a customer gave you the wrong specifications, or somebody asked for the different behavior. You're writing a medieval war game, and then somebody asked for lightsabers to be included in it. Okay, that's going to take considerable revision of what it's supposed to do. You'd have to go back to the definitions and change those things, and so that'd be a big change. Correct any errors found. Repeat all these steps. Wash, rinse, and repeat. Validate the results of the program, and then once you're sure that it works, then in a production environment, you would give that to a QA team, and they would repeat the tests. And if they find problems, you have to go back and you have to fix them. But, in this class, we're testing our own programs. Then it shift off to the customer, and they find all the problems that your QA team missed. So the difference between procedural and object-oriented programming, it's a huge, much larger topic than we could talk about in 2 bullet points on a slide. But procedural programming is what we're going to learn first. Procedural programming is pretty much what we did in Python. We just tell it what to do one step at a time. We focus on the process. I need my program to get some data from the user and then multiply those numbers together and then present the output. While object-oriented programming is the idea that you focus on data and what that data means and what you could do to it. So you have an employee class, and an employee has a name, and an employee has an age, a birth date, an insurance plan, hire a date, a fire a date, a position, a salary, all that kind of stuff is an employee. And so you make a class that contains all of that stuff. And then you decide what needs to be able to happen to an employee. I need to be able to enter data for the employee. So you would write some code that does that. And I need to be able to print the employee. And I need to be able to save that data to disk or read it from a database or whatever. So you create your data, and then you decide what functions need to happen to that. And that's a different idea than the idea of, top-down programming, where you're going to start, you're going to get some pieces of data, and you're going to perform some loops or whatever, and you're going to do some output. Do you have to use object-oriented programming to write awesome programs? No. Linux. The Linux kernel is not written in C++, it's written in pure C, because Linus Torvalds thinks, and I'm sure that he's right, that pure C is easier to debug and to understand conceptually and to prove that it works without causing bad side effects or bugs than a C++ program. And so it is, the operating system itself is written in C. However, the applications that run on it are probably all written in an object-oriented programming language, because you can build very complex programming languages. These graphical user interfaces, Windows and Excel and Word and PowerPoint and your big games could not be written really without object-oriented concepts. Object-oriented concepts. You have a character, in World of Warcraft, and he has these attributes. He has a strength and a spell-casting abilities and stuff like that. That's the idea of a class. It's kind of similar to your gameplay that you thought about, except it applies much more to just characters. Alrighty.
So are the object-oriented, is that like dictionaries in Python?
Dictionaries are classes. You're correct. They are data structures. Absolutely. Right. Okay. Usually I'm not going to lecture for an entire session because that gets boring, right? Some of y'all are already itching to check Facebook or probably already are. But I know, Facebook's for old people. Who uses Facebook anymore? Y'all are all Snapchat users or something. So, but are we going to code stuff? I don't think that in the next 12 minutes, including taking time for taking roll, which I don't think we would have time to write a good program. So let's go ahead and look at PowerPoint 2, but we're not going to spend too much time on it. Do we have any programming homework based on Chapter 1? No, and I'm not going to give you a quiz over Chapter 1. I probably should, over the idea of compilers and stuff like that. Never done it in the past, though. So your homework's going to start rolling in the assignments as we hit Chapter 2, because that's where the actual language, rather than just the concepts, starts being introduced. Tell you what, why don't we